sign. This right here, you know, we have this slope of, and I got nothing written there. This is known as an operator. This is too, but it's a lot simpler. So that's what an operator is. We can go one step further. Negative h bar squared over 2m nabla must be nabla squared.
So it's just a triangle, just a crooked triangle.
It's supposed to be an upside down triangle.
But it's an equilateral triangle, so there is no.
This is known as the nabla.
Obviously.
I think you calc 3 is when you actually get into it. Or in physics 252.
Would you divide both sides by side? Just get it equal to E?
No.
Okay.
Because the operator has to operate on something. And
Now if you do it to the side, that's not.
yeah, it's like if I have sine of theta, I can't just divide out the theta. It's linked to that operator sign.
So you said calculated, you use the symbol as a number, or is it a function?
It's just trying to think of sort of an equivalent or analog that you would have seen. It's like a function machine. Yeah, it depends on who your math instructor was, whether you talk about function machines or not. Function machine. You put stuff in, stuff gets kicked out. So if I put in a 2 and I get a 4 out, I put in a 3, I get a 6 out, I put in a 4, I get an 8 out. What is the function machine doing?
2x.
Yeah. So y is equal to 2x. There's my y's, there's my x's. So it's sort of like that. 2 is operating on the x. This is a little bit more sophisticated because I'm not multiplying, but I'm actually doing something. So if I had my function machine, I put in sine and I get out cosine. If I put in cosine, I get out negative sine. I put in negative sine, I get out negative cosine. I put in cosine, negative cosine, I get out sine.
It's taking the derivative.
Yeah.
But is there like, is it nabla do the same thing all the time? Like, or
It's doing the second derivative with respect to space.
okay, that makes sense.
Okay.
Other than what is just space?
As opposed to time. In reference to x, y, and z.
Okay.
It is technically, nabla is a vector operator, and it is I hat del x plus j hat del y plus k hat del z. That is what it does.
Those aren't twos.
Those are not twos, those are dels.
Okay.
It is known as taking a partial derivative,
Okay.
which conceptually is more difficult than derivatives, but mechanically, what you have to do is so much simpler than regular derivatives. But that is, again, beyond the scope of the course.
I believe.
Okay.
Wait, so why don't we use, hypothetically, why don't we use like something like a del instead of using like the same Greek letter 800 times?
Why are we using del instead of?
No, I'm saying like, what's the one that there's the video of all the different Greek letters that it means? Because it can mean a bunch of different things.
Oh, mu.
Yeah, why don't we
Oh.
use that and replace some of the mu's? So we have like 10 mu's.
Because this comes to us from the math people,
Okay.
and no physicist. Well, I was about to say no physicist was arrogant enough to change it, but that's probably not true. No physicist has bothered to change it, or if some did, it was never accepted. All right, so I now have an idea of a wave function. This is the wave equation, and so if given a situation if I can find something that satisfies this, given boundary conditions, in essence, I have the wave function for a particular object. Also, this wave function, what exactly is it? Well, it's a mathematical description such that if I, whatever the wave function actually ends up being, if I square it, this is the probability of a particle, I guess of x, of a particle being at position x. Again, guessing this idea that that's what quantum physics tells us is basically probabilities. So if I have a wave function of an electron, if I square it, I now have a formula for what my best bet of where the electron actually is. This interpretation of it was decided in Copenhagen in the 20s, I believe it was, late 20s, and it's known as the Copenhagen interpretation.
You don't think we can do a plug-in chart for this one?
Let's do a plug-in chart for this one. Taking a quick gander here to see how much calculus we need to handle today. Now we got it.
I mean, you already taught us the first 3 rules, the biggest 3 rules. Do we need chain rule?
Do we need what?
Chain rule?
In
Hand wave the math, you don't have to do it.
let me get through at least one of those. That's probably not the best one. Here we go. We'll do this one. All right. I introduced to you the infinite well, the infinite one-dimensional well.
As in just a hole that goes on forever?
Yeah. And the reason why it's infinite is that if this is my potential versus position graph, basically it is equal to 0. There's absolutely no potential down here, but I have infinite potential here so that it can't escape. It's the hole that nothing can escape. I know that negative h bar over 2m plus v psi is equal to e psi. And so imagine that I have some particle of mass m that is stuck within this position here, so that is L. So between 0 and L, this particle can exist. I know that, well, we'll get to the boundary conditions in a moment. So I'm starting out with a generic value for this. I know it is a wave that is cyclical, and so I'm just going to do A, and just to keep in league with my notes, let's make sure I'm using the same, which one's which, okay. A times the sine of kx plus b times the cosine of kx. Just a generic wave equation. I'm now going to introduce my boundary conditions. I know that, that's y of x, that psi of x, psi of 0 equals 0. The particle cannot exist at 0 because it's got an infinite wall right there. I can be really close to it, but I can't. But it can't exist at 0 and L. And so if I plug this in for x, I have a sine of 0 plus b cosine of 0, which is just b. And so now I've eliminated half my equation. So my wave function now has been reduced to a sine of kx. I now plug in psi of L, my other boundary. That's equal to 0 there. The wave cannot, the particle cannot exist at L because I've got an infinite wall right there. And that's going to be a sine of KL. So the question is, when is KL, or for what values of KL will the sine of KL be equal to 0? The sine of what is equal to 0?
Sine of 0 is equal to 0.
Okay.
1.
No.
Pi.
Okay. 0, pi.
2 pi. 3 pi.
And so on.
4 pi.
Plus or minus. So as long as, and n is just, so n is just an integer, so n is an element of integers. And so we end up with k is equal to n pi over L. I guess I don't need a plus and minus if I'm just saying it's an integer. You see my equation here? So I have negative h bar squared over 2m. I have a generic equation of my graph over here, of my wave function. So it's some amplitude times the sine of n pi, sine of n pi over L times x. This is the slope of that over there. So this is going to be A times negative sine of, gap right there. We have n pi over Lx, n pi over Lx, and then here we have an n pi over L squared. That's just slope of the slope, we've done that before. Plus, if I'm in the well, my potential is 0, so this term drops out and I'm just left, so plus 0 is equal to my energy times psi.
You said if you're in the well, the energy is dropped out.
Yeah, because my potential, inside the well, my potential is 0. Everywhere around here, it's infinite at the sides, so my potential energy drops out.
So, okay, so like in the space between, it's 0.
Yes.
Okay.
Yeah. So equals E psi, we can actually do better than that. Times sine of, or A sine of n pi over L x. Well, let's get rid of some stuff. We will pretend that one of these markers will highlight or mark or erase. Sine goes away, A goes away. And so now I have a formula for energy of this particle. So the energy of a particle in an infinite square well is going to be, well, what I'm left with is negative h bar over 2m n squared pi squared over L squared. Or, writing it in a slightly different form, negative h squared over 2m pi squared L squared n squared. So I have some base energy here. So if n is equal to 1, my energy will just set equal to E sub naught. So I've now reduced this into E sub naught n squared. And so whatever my base energy is, if I square, then 4 times that would be the next energy level, 9 times that would be the next energy level. So if I were plotting energy first time, energy, this is n is equal to 1, n is equal to 2, my energy here would be E sub naught. This is 4 E sub naught for n is equal to 2, 9 E sub naught for n is equal to 3, and we get bigger and bigger gaps between the energy levels.
Incredible.
My base function here, if n is equal to 1, then my equation, if n is equal to 1, this just becomes my amplitude sine of pi over Lx. If I plotted that out, that is just that. If I squared it, it'll look something like that. And there's my probability function. At energy is equal to, at n is equal to 2, we're now here. My plot, well, I have it 2 in place of n, and my graph looks like that. If I squared it, most likely the energy, if it's in that second energy level, the particle would be here or here, most likely.
Huh? Wouldn't it be in the center? Or like,
No, because if I look at that, it's equal to 0 there. My function's equal
Oh,
to 0
zero,
there, and there. And 9 at E sub naught. So when I'm here, I now have my wave function looks like that. And if I squared it, I've got 4 places where the probability of the particle existing is 0. So hopefully you can see some sort of, we can now make some predictions here. I did talk about walking through walls, so let's walk through a wall. So I got an infinite potential there. And then I have a finite potential here. If I created the wave function, my wave function cannot exist out here because my infinite potential, it can't escape. But if I have a finite here, then what's going to happen is my wave function is going to start, it will exist inside the barrier here, but it starts to peter off. If I now made this finite part of the well a finite width, if I have a particle in a well here, well, it does sort of peter off, but if this barrier is short enough, it can exist outside. So if I have an infinite square well, there is a possibility that, let's say I have an electron in an infinite square well, there's a possibility, in a finite square well, there's a possibility the electron could actually exist on the other side of the barrier. It doesn't, with mechanical energy, stuff that we have done in the past, you have to overcome the barrier in order to get out. Quantum physics tells us you don't have to actually go over the barrier, you could go through the barrier. This is known as quantum tunneling. And it is the basis of the electron scanning microscope. Electron tunneling microscope, sorry. What you do is you have a barrier, you basically send electrons at the barrier, and then depending upon the thickness, you have, if it's very thin, you have a much higher probability of an electron escaping than if it's thicker. And so you can start to get some idea of thickness of barriers by how many electrons manage to make it to the other side. So, if I throw a ball against a wall. There is a possibility, a non-zero probability, that that ball is going to quantum tunnel.
What?
Now, I've not heard about this, but would that just be one layer of the ball or the whole ball?
Each one would have to quantum tunnel.
So it would be,
Odds are against it, not within my lifetime. But the probability is not zero.
it's still
It's
there.
incredibly tiny, but it's not zero.
Okay,
And that's
so-
for each atom?
And that's considered like,
Object?
Yeah, I mean, each atom would have to quantum, each part inside would have to quantum tunnel.
wait, so that's if we're treating the ball as a wave.
There's certain wave properties to it, yeah.
So what happens if part of the ball quantum tunnels in the other part? Does it just break apart?
It would. Now,
Would it like actually cut in half, or would the part that quantum tunnel like break apart by each atom?
well, considering the odds against it actually quantum tunneling, if we might actually bounce the ball against the wall and some of it, and you know, you might get a particle quantum tunneling, and we would not notice. If we had a significant portion, then it is possible that, you know, bits of patches of the wall would go through and the rest of it would stay behind. But recognize we now have two ways of actually going through a wall. One, quantum tunneling, and the other one is to align all the particles so that they are all spin integers, because electrons and protons are spin half particles. But if you align the electrons and protons right, you can get a spin 1 or spin 2 particle and so forth. And spin integer particles can pass through other spin integer particles. That's why light doesn't bounce off itself. Light can pass through. Light's a spin integer.
Well, when I figure that out, I'll get back to you. As in how to do it.
So you just have to give yourself spin integral particles, make yourself a spin integral particle, and the wall spin integral particle, and then you just pass right through.
And then the method of doing such, well,
They haven't figured that out yet.
that's the dark side of physics.